In the first section, we've talked about vector spaces in a general manner. We have defined the properties and the condition that create this environment, but nothing more. In this third section, instead, I want to study in deep how the elements of this environment generate and give them some particular properties. In particular, we will study the bases, which are the skeleton, in some way, of a vector space. But let's start with the concept of linear combination. Let's take k elements of V and k real numbers. We define linear combination as the summation, the sum of these vectors multiplied by their scalar number. We can do this, remember, we can do this always thanks to the vector space properties. In fact, this vector that is computed between this linear combination belongs to the vector space, thanks to the, in particular, to the distributivity property. What we are doing with the linear combination? Well, we are building a vector that belongs to the vector space from a set of other vectors, which are the x vectors, x1 to xk. Pretty interesting. And we can always do something like this. We have just to define the x vectors and give them some coefficients. Now, thanks to the concept of linear combination, we can define what is linear independence. When the vector is the neutral element, we are getting this condition, and we say that if this condition is satisfied only if all the coefficients are 0, then the k vectors are said to be linear independent. As we will see in a few minutes, not all combinations are linear independent, because, for example, we could have two vectors that, given some coefficients, simplify together, and the coefficients are not equal to 0. So there, we will say that these vectors are linearly independent. Let's take an example in R2 of linear independence. And I want to show you how these two vectors, E1 and E2, are linear independent. How we can test it? Well, we take the linear combination and we put the result equal to the R neutral element, which is 0, the 0 vector, of course, in R2. So two components that equal to 0. This equation could be written as a linear system where you can see that since we have some coefficient equals to 0, the result is simply and inevitably that the two components, the two coefficients, need to be equals to 0, both equal to 0. We have just proved that E1 and E2 are linearly independent. But as I was mentioning before, not all vectors, all set of vectors are linear independent. And let's take a look to this combination of three vectors in R2. We keep E1, E2, and we add to our set, we include in our set this vector V. Again, to test if these three vectors are linear independent, we just compute our linear combination, pointing out that the result should be the neutral element. Solving this equation is not that as simple as before, because now we have this lambda 3 coefficient that does not equal to that is not always multiplied by 0. So before we had v that equals to 1, 1. So here we have lambda 3 multiplied by 1 in the first term and in the second term. Here, as before, the component of E1 and E2 equals to 0. This this system of equations can be satisfied in several ways, taking several values of lambda 1, lambda 2, and lambda 3. For example, we can find that putting lambda 1 equal to 1, lambda 2 equal to 2, and lambda 3 equals to minus 1, then this system of equation is always satisfied, of course, because this equals to 1, this minus 1, result 0. 1 minus 1 equal to 0. We have solved our linear system, but we have found that to solve this linear system, we used coefficients different from 0. That's the case that violates the linear independency property. So these three vectors here there are said to be linear dependent. So we can see that the vectors are linearly dependent if and only if at least one of them is a linear combination of the others. For example, it's pretty simple to see that V now is a linear combination of the other two elements, the other two vectors. We just have to take the both coefficients equal to 1. That's it, pretty simple. So when we have a linear dependent set of vectors, we can say that at least one of them is a linear combination of the others. But we can say that if we take a set with one vector that is a linear combination of the others, then the set, of course, will be linearly dependent. As we have seen in the case of R2, to test if k vectors are in a generic space are independent, we need to solve a system of linear equations. That's how we defined the linear combination, of course. But as we have already done, for example, in the section of matrices, we can rewrite this equation with a matrix representation. Now x becomes the k-axis became a matrix. As you can see, every vector here is a column. We have the first column, which is this term, and for example the kth vector, that is the kth column of the matrix. The coefficients are written as a column vector, and 0 is also a column vector. Then, to solve this linear system, we can use the usual methods that, of course, I remember to you, we have not explicitly studied. If we find, after solving this linear system, that the equations are satisfied only if the coefficients are equal to 0, then we find that the k vectors are linearly independent. Now, in the next 2-3 slides, I want to show you how we can represent, following the previous slide, how we can represent a set of linearly independent vectors. For example, let's take these b1, bk linearly independent vectors. And thanks to linear combinations, we know we can write a generic element of the vector space as a linear combination of this. Nothing special, we've just written a linear combination, but with some particular vectors, because those are linear independent. Okay, we have m linear combinations, because, for example, we want to represent m vectors using linear combinations of these kb vectors. We can then rewrite, as we've done before, these linearly independent vectors in a matrix, where every column of the matrix is the linearly independent vector. Just it. Of course, in the previous slides, we have tested the linear independence by putting this equal to 0. Now, since we know that in B there are only linear independent vectors, we can express the linear combination as here, as a matrix multiplication between matrices, or better, a multiplication between a matrix and a vector column. Very simple. Now, if we take k vectors, we build a linear combination, and we can build a linear combination that represents every vector in V. So we can write this equation for every V in our vector space. Then this set x1, xk is said to be a generating set. Given those k vectors, we can define every vector in the vector space. Pretty powerful condition. We just need k elements to define a potentially infinite number of elements of vectors in the vector space. We just have to take those vectors and multiply it with scalars and sum every term together, and we get a new vector in our vector space. Very powerful notation. In fact, we say that the set of all linear combination of vectors computed using these k vectors is said to be the span of V. So V in some way can be generated, can be spanned thanks to these k vectors. Very, very useful and powerful concept. The fact that using a finite number of elements, we can build a potentially infinite vector space. Very powerful. But we can do better. And For example, we can take these three vectors, say that they are generating set, but we can notice that here some generating sets could be linear dependent set. So if this can be written thanks to this, then we can delete this term and say that these two can define this term and the rest of the vectors in the vector space. So our goal is to try to find the minimal set of vectors that span our vector space. So every linearly independent generating set is minimal and is called basis of V. Here we finally define the basis of V. What is? I explain one more time. Well, a basis of V is a generating set, so the set of vectors generate all the other vectors in the vector space, but has one more property, that is minimal. So it's the smaller set that can span that spans B, and we can find that this set contains only linearly independent vectors. Of course, because if the vectors are linear dependent, as we already seen here, then this vector could be written thanks to these two. So we don't need any more V. We can just think about these two. So thinking more deeply on about bases, let's take K vectors that are bases. We can say that thanks to linear combination, every vector of V is a unique combination of V. So the coefficients that we use to express a generic element in thanks to the elements of the basis are unique. As you can see, here are two ways to write the same thing. Well, if these B are basis vectors, then the coefficients are equal. This is even more powerful than the generating set, because we have a minimal generating set, and given this basis, we can write the vector and every vector of the vector space in only one way. But, that's a but, given a vector space, we can find multiple bases. For example, here we are looking again at the vector space R2, but here are the two vectors that we are already seen, and these are two generic vectors that are both bases. The same vector so can also written in two ways using two sets of bases. The result is the same. Of course, the coefficient used to compute the linear combination depends on the basis we are using. For example, these two vectors that we already find as linearly independent are said to be a canonical, standard, and natural basis for R2, for the plane. Here, in the left picture, we are using, in fact, those two vectors as basis. But I repeat it once again, we can find on the plane or on whatever vector space multiple bases. So a basis effectively defines a coordinate system, so the way we see our vector spaces. In the picture, you will be surely familiar with the Cartesian coordinate system in 2 dimensions. And this coordinate system is spanned by the canonical basis vectors, these 2 vectors. In fact, when we draw a Cartesian axis, we always draw the x and y axis, and the bases are the canonical bases. But as we already seen, we can define some other bases that are still a valid coordinate system. So, the same vector, we change the basis, can be written in a different way. Of course, because the coordinate representation changes. The coordinates are the lambdas that we are using, the coefficients. What we have found in this section is that the basis is the skeleton of a vector space. How we perceive the vector space. And also, thanks to the concept of generating set, minimal generating set, if we take a basis, then we can build the entire vector space. We can explicit the entire vector space by defining just its basis. A very, very powerful concept. And this concept will be leveraged in the next section, the linear mappings, when we will use the basis to change the way we view the vector space. We are in the linear independence and basis section, we have seen that the vector spaces can be interpreted using bases, which are our point of view, the way we perceive and view the vector space. Now our goal is to change the way we view the vector space. And to do so, we will talk about linear mappings.